This week we're going to look at sensitivity analysis of linear programming problems. So this concerns the question as to the degree to which the optimal solution depends upon variations in the cost coefficients and the resource values. If we vary the cost coefficients or the resource values slightly, will the optimal solution change radically, or will it just change a little bit? We don't look at changes in the constraint matrix, the matrix A that we've been looking at. We only look at the cost coefficients and the resource values, and we'll only look at one of these at a time. We'll just look at changing a single cost coefficient or a single resource value. This will certainly give you the idea of what the main concepts are and how things work. And we've only got 1 week on this, but you'll certainly get to see the key ideas. What we're interested in knowing about is what small changes can be made without the solution being fundamentally affected. And we call such changes the allowable increases and the allowable decreases. So we'll see theorems that tell you exactly how to compute these. Changing a cost coefficient. So if we've got a single cost coefficient Ci and we change it, we won't be changing at all the feasible region. Remember, the cost coefficient just appears as a coefficient in the formula for the objective function. The feasible region, however, is determined by the constraint inequalities. So changing the cost coefficient doesn't change the feasible region, but it will change the slope of the level sets of the objective function. Now, if the change in slope is small, the optimal solution will still occur at the same corner of the feasible region. But if the change in cost coefficient is too great, suddenly we might find that the solution jumps to a completely different corner of the feasible region. So we want to see how much we can change the cost coefficient by without this happening. And this is presented in theorem 6.1 of the printed notes. In order to present theorem 6.1, I just need some notation, and there's 2 forms of notation that we'll need, one for the cost coefficients and one for the resource values. And they both concern the final tableau that we obtain when we do a linear programming problem. So the final tableau is written in 2 ways in the printed notes. In one way, we separate out the decision variables x from the slack variables s, and the numbers that appear underneath the decision variables, we denote that block A star, and the numbers underneath the slack variable we denote K, and then this is the bottom row, so this is the objective function row, and the numbers here are denoted D and U transpose. U transpose because U is the solution to the dual problem. And then here we have B star are the numbers that appear in the resource values column, again in the final tableau. And here the optimal solution Z star. Alternatively, sometimes it's convenient to group the decision variables and slack variables together. So if we put them all together, then the big matrix, which is formed by A star and K, we denote that E, and the long vector D followed by U transpose, we denote that F. So the theorems will refer to these blocks of blocks of numbers and vectors. And here is theorem 6.1, which concerns what happens when we change one of the cost coefficients. So we're going to change cost coefficient Ci. So I is fixed here. It could be 1 or 2 or whatever, but it's a fixed thing. I is fixed. And you notice that the theorem depends on whether or not the corresponding decision variable xi is basic or not. So there's 2 parts of the theorem. The first part is when x is non-basic, and it says that in this case, the allowable increase in the cost coefficient is the number fi. But f's this vector here, and fi will just be the entry of f in the I spot. So this is the entry corresponding to the cost coefficient ci. And there's no restriction on the allowable decrease at all. No, you can decrease ci as much as you like, it won't change the solution. When x is a basic variable, well, in that case, because xi is basic, there'll definitely be a 1 somewhere in the I column. So let's call that particular row the jth row. In that case, there's these two expressions for the allowable increase and decrease, and they're both minimums of certain sets of fractions. And they are in fact ratios fk over minus ejk. So you notice here, j, that's fixed. That's the row number where the 1 occurs in column I. And what we're varying here is the k. We're taking the minimum over k. So we're letting k vary, and we're computing the ratio fk over ejk. Now for the allowable increase, we're looking at ejk less than 0, so minus ejk is positive. And in the second case, we're looking at ejk greater than 0. And again, so this again will be positive. So in each case here, the denominator is positive. And the fk are the numbers that appear in the bottom row. And in the final tableau, they're always positive. So these ratios will always be positive. And we're looking at the minimum. Okay, so what are we doing here? We're looking at the minimum of fk divided by ejk. So j will correspond to some row, and we're looking at ratios, ratio of fk over ejk. So we're running across a row, and we're looking at the corresponding f entry divided by the corresponding e entry. F entry divided by e entry, f entry divided by e entry, and so forth. And we take the smallest of the ratios. Now, this theorem will be given in the formula sheet on the exam, but of course you need to know what the e's and f's are in order to use it. Little thing here, if it turns out that the set is empty, for instance, in the second case here, suppose none of these numbers were positive, then we'd be looking at the minimum over the empty set, and the minimum over the empty set is defined to be infinity. That is, no restriction. So that's the cost coefficients. Now for the resource values. When we change a resource value, this time we're not changing the level sets of the objective function, but we are changing the feasible region. And it's a similar kind of thing. It's actually kind of a dual situation to the one we've just looked at. But again, the same question arises. What's the biggest changes we can make which don't fundamentally change the solution? So this time, as we vary the BI, the fundamental region will change slightly, so the corner point will actually move. But as long as the geometry doesn't change too much, the solution will only move a little bit, and it won't jump to a different corner. This time, the theorem that's important is theorem 6.2, which gives us the allowable increases and decreases in resource value BI, and it's a very similar appearance. You notice though that we don't have to worry about whether anything is basic or non-basic. This theorem is a little bit easier really. But the expressions are very, very similar. In one case we're looking at something being negative, in the other case something being positive, and we're looking at a ratio here, and the numbers will always be positive that we're looking at. The ratios will be positive, and we just take the smallest one. So what are we looking at here? The BJ's over the KJI's. Well, the B's are the things that are in this column, and the K's are the things that are under the slack variable. So previously, for the cost coefficient, we ran across a row and we computed ratios. Now we're running down a column. We run down the ith column and we compute the ratios going down the column. The ratios between the B's and the K's. Now, explanations, some discussion as to why the theorems are true are given in chapter 6. They're not formal proof, but they certainly give you the important ideas, and it's actually not difficult from that to make rigorous proofs. You won't be asked to do anything theoretical with these materials. We've only got 1 week on sensitivity analysis. So what I'm hoping is that the students will understand what's going on here, and in particular be able to implement these 2 theorems. So you should definitely go along to the practice class and look at the work problem solutions on LMS, which give you some examples of exam type questions. As I said, these theorem 6.1 and 6.2 are given in the formula sheet on the exam. Most students don't really work directly from the theorems. Once they've done a few examples, they just remember the process. They remember the process for the cost coefficient. You run across the row and take the ratios, and they remember that for the resource values, you run down the column and you compute certain ratios. And if you do enough examples, it's just like riding a bike. You'll just remember what to do.